Thank you very much. Good afternoon, everybody. It's great to be here. So before I get started properly, can I just point out I've already put the slides online. So if you want to follow along on your laptops, you can just go to martinkl.com/strata, and the slides are already there. So just as a convenience for you, if you like. OK, so I'd like to talk a bit about data agility, which seems like a fairly buzzwordy thing. So let me just explain first why this is at all something worthwhile talking about. So you're probably familiar very much with agile as this concept from project management, where the goal is really, to put it in a nutshell, to try and be responsive to changes in requirements. Because most of us work in environments where we're not even quite sure what problem we're solving, so the solutions that we build for problems have to keep evolving and changing and adapting to what we learn. And so thus the software development process has to be suitable for that kind of environment where you've got a lot of uncertainty as to how things might change next. But, well, when you come to data, I feel that we haven't really thought as much about agility as we have in the kind of application development and deployment sort of area. Because the problem with data is that it's fundamentally quite an unagile thing, actually. If you have if you have a lot of data, even just moving it around is difficult. Changing its schema can be difficult sometimes. Deciding that you want your data represented in some kind of different form can all be difficult. And so at the moment, our tools for changing your mind about requirements of how your data is represented and stored and processed is actually still fairly hard. And so we've been thinking about this kind of thing. I used to be at LinkedIn, and LinkedIn has quite a bit of data, as you can imagine. And so I've been thinking about these problems. And what I'd like to relay in this talk is some of the lessons that we've learned of how to think about data systems in such a way that hopefully we can be more agile at software development using that data. So at the moment, I'm taking a sabbatical, actually, and writing this book. It's called Designing Data-Intensive Applications. And if you're interested, it's not finished yet, but we've published the first 7 chapters so far online at dataintensive.net. So you've probably seen this Maslow's hierarchy of needs before. People love to quote it. The basic gist of this is that there are various different things that we humans tend to aspire to, but they come kind of in a priority order. So like your self-actualization, the realization of your true self and your beliefs is a great thing to aspire to. But if you're hungry and thirsty, you probably don't care about it very much. So only once food and water have been sorted out do you worry about the next level up. Once your kind of basic physical security and things like that are satisfied, then you start worrying about the higher levels and so on. So I was kind of idly thinking, what if you adapted this kind of thing to a hierarchy of needs in a data-driven organization? And it seems to me that at the top it's got some sort of high vision, some kind of great mission for what your organization is trying to do, how it's trying to change the world. But how do you actually accomplish that? Well, probably you make some kind of products or services, and hopefully they're useful to people. But in order to build those products and services, assuming they are somehow data-related, there's some kind of data processing going into them, well, there's probably some intelligent analysis and analytics of the data that has to happen. This is what we call data science, for example, of munging the data, understanding it, making sense of it, deriving useful things from it. But even the most fancy machine learning algorithms have to run on some kind of infrastructure. So you can't start doing fancy processing before you've got some sort of just servers and machines and tooling in place in order to be able to do that. But even the infrastructure, even the fanciest Hadoop cluster is no good if you don't have any data in it. So really the most basic requirement here is to simply get hold of the data, which sounds like this really mundane thing, but actually even that isn't really a solved problem yet. You know, some people add Wi-Fi as the bottom of this pyramid. You might have seen that one before. It's been circulating on Twitter. I guess you need Wi-Fi for data access as well. So the problem why simply getting hold of the data is hard is that it's fragmented across all of these different places. So you've got various different online OLTP databases which are storing transactional data for the services that are actually serving users. But then the applications, as a side effect, throw off some logs. Those logs, they may be on files somewhere on disk, or maybe they're in some kind of syslog or log aggregation thing. It's probably this separate thing somewhere on the side. Maybe you've added some new non-relational databases to the mix, so they're yet another place where some data sits. And then maybe you're doing some messaging via message queue, or even some kind of enterprise service bus, God forbid. All of these things carry data and keep them for varying lengths of time. Don't forget about search indexes and maybe your monitoring systems and so on. So all of this stuff is fragmented all over the place. And I can hear you thinking already, well, hang on, we heard that story 20 years ago already. We're talking about data warehouses. And indeed, data warehouses are still very much a thing, and they're not going away, certainly. And now, of course, Hadoop and Spark and so on are kind of the next evolution in that kind of area. And the idea there is that you have these various disparate data sources, and you pull them together into one central place. And that process of pulling it together is called ETL, where the E is extracting it from the source database, which typically is done as a dump of the entire database. So this is maybe something that you run once a day or once a night. You copy the entire contents out of the database. Then you probably transform the schema, because the kind of data format that is good for operational purposes is often not the same as the kind of data format that's good for analytic purposes in a data warehouse. So it makes sense to have some kind of transformation, translation step there in between before you load it all into the data warehouse. If you look at how the ideas of data warehousing evolved, so since the early 1990s, when folks like Ralph Kimball started talking about these ideas, things have evolved quite a bit. So in the big change that happened as we went towards Hadoop and HDFS and MapReduce and Spark and so on, a couple of things changed. So one of the things that changed is that people stopped assuming that all of your data has to be relational. And don't get me wrong, I think the relational model is still very powerful. If you're doing business analytics type things, some kind of star schema still works really well. There's still a lot of use for that. But not all data necessarily has to be that, in that shape. And when people talk about unstructured or semi-structured data in Hadoop, that's really all they mean is allowing data that's not in a relational schema. And that's totally fine as well. In fact, it may even make sense to have that transformation part of the ETL pipeline and do that in something like Hadoop or Spark so that you can just take that raw step of extracting the raw data from the database as step one and separate it, have it less conjoined with this step of transformation. So that's one of the things that changed, is we stopped assuming relational for everything. Another quite important thing that changed is the programmability and flexibility of these things. So again, a data warehouse is great if you want to run SQL queries, which is what you want to do if you're a business analyst and you want to do some reports on sales forecasting or figure out whether a particular promotion has worked or so on. So that all makes sense. But if you want to train a recommendation system and run some machine learning algorithms, or if you want to try some other algorithms that are not built into a data warehouse, then the facilities for doing so are very, very limited. And that's part of where the appeal of things like Hadoop came in, is it allowed you to run arbitrary code. You could just write any kind of code and run it on large data sets. And thus you can experiment with new ways of processing things. So it just added an extra part. And of course, the other thing that changed is that we moved from a kind of proprietary software packages more towards open source. So the next step of this evolution that I see happening here is more towards real-time data, because fundamentally, all of the previous tools are still quite batch-oriented. That is, the data that's coming in from your database is probably a daily dump of the entire database contents. That doesn't really help you if you want to respond to things that are happening within a second or two. Similarly, what's happening is that we're seeing requirements for systems that are continuously responding to activity that's happening. So take a fraud detection system, for example, which wants to, with fairly low latency, figure out whether something's going wrong so that you can block the person. You can't do that the day later. By then, it's far too late. So we're moving here from a world of batch processing towards a kind of real-time, low-latency stream processing. And this is really where tools like Kafka come in. I think probably a lot of people here have heard of Kafka before, have you? Cool, excellent. So I don't need to say too much about it. I'll just summarize it briefly in case somebody hasn't seen it before. The basic model of Kafka is that you're dealing with streams of events. And an event here is simply something that happened. It's recording the fact that something occurred. And a stream simply means that if you're interested in learning about the fact that something occurred, you can subscribe to that stream of events, and then you get notified whenever something happens. So as such, this looks pretty similar to message queues, really. I'll explain the difference in a moment. So the kind of things that happen are, for example, like lines from a web server log. This is, for example, one line from an Nginx log file, I think, and it has the IP address of the client and the date and time of when the request happened and the URL that was requested and the response code and the referrer and the user agent and so on. And this is here in a text format. You could use some other kind of encoding like Avro if you want. Doesn't really matter too much. Kafka doesn't care what format the data is in. So the interesting difference of Kafka compared to, say, RabbitMQ or other AMQP-based message brokers, or compared to, say, JMS message brokers, is that Kafka's the underlying concept of how it's built is very similar to a commit log in a database. And it looks somewhat like this. You can think of Kafka as basically these append-only files. So the only way you can write to Kafka, i.e. send a message to Kafka, is by appending it to the end of one of these long files. So there's no way to go and update an existing message somewhere in the middle of this stream. The only write operation it supports is appending to the end of it. That restriction actually is a blessing in disguise because it allows it both to scale very well and also enables some really interesting processing, as we'll see later on. If you want to read from Kafka, there's only one read operation. The only read operation is given an offset into this long append-only file, i.e. a file position, read messages sequentially from that point onwards. That's the only thing you can do. So if you're a consumer, if you want to follow the latest messages that are happening in a stream, the consumer is in charge of keeping track of its offset in this long file, and it just asks for messages from the last offset that it last saw. And if the broker hasn't received any more messages in the meantime, then it says, no, nothing there. And if it has, it'll return the messages. And then there's a bit in the protocol so that it sends push notifications through to clients. But the basic principle is just this. Now, let's talk a bit about one more thing to mention is that it's partitioned and replicated, of course. So if we want the thing to scale, it has to run on more than one machine. If we have more than one machine, then we have to account for the possibility of machines failing, and we don't want to lose data if machines fail. So Kafka you can think of as not just one append-only file, but actually lots of separate files. Each file we call a partition. And so within each of these partitions, all of the messages are totally ordered. So they're fixed order in which the messages appear. But across two different partitions, there's no guarantee of ordering at all. And so this means that you could put all of the related messages together in one partition, but two different partitions can live on two different machines, and each is then also replicated across multiple machines. So that way you can scale the whole thing over a cluster of machines. And it actually works very efficiently. LinkedIn pumps like well over 10 million messages a second, I think, through Kafka. So let's talk a bit about the kinds of things you can put in this kind of message broker like Kafka. What are the types of events, the things that can happen? Well, obviously a thing that can happen is if you have a web-based application, users can click on things, and you might want to record the fact that at a particular time, a particular user clicked on a particular thing, because that's interesting information for analytics, and you can use it for A/B testing. You can use it for figuring out which features are working, which are not. You could use it to train recommender systems, and so on. Many things that you can do with it. Another thing you could do is for more sensor data-like things. So I dare not say Internet of Things, but if you want to, it kind of fits into this category. Or it could be something as mundane as the CPU utilization on a server, which gets reported every couple of seconds. So simply a tick in a time series, again, is a type of event. And then one thing that people tend to not think about as much, but I think is actually the most interesting, is database change events. That is, anytime somebody writes some data to a database, that is in itself an event. That's recording the fact that some row was inserted or updated or deleted in a database. And the fact that when that happened and which user did it and other metadata like that is in itself interesting. So actually capturing the stream of databases is a very valuable thing to do. And there have been some tools that try to do things. It's kind of falls under the general headline of change data capture. And you get stuff like Golden Gate for Oracle, I guess, or for MySQL, there's the bin log if you can figure out how to parse it, or MongoDB has the oplog, and so on. They're not very well integrated, very, very easy to access systems yet, but in principle, at least, you can get a stream of writes out of a database. I just released a little open source project just a week or two ago called Bottled Water, which does this thing for Postgres. So if you're users of Postgres, this might be interesting to you. What the thing does is it takes a consistent snapshot of all of the data in Postgres and then also hooks into a new write-ahead log decoding facility so that it can be notified whenever inserts, updates, and deletes happen. And all of this stuff is then replicated out to Kafka. And then anyone who wants to consume it can take it from Kafka. It works kind of like this. So you install a little plugin inside the database server and have a daemon which connects to it. I won't talk about it too much because I get into a bit of detail, but this idea of capturing database change data and putting it in the same model as all of your other streams, I think, is really powerful. So returning to this pyramid here of needs, what I've been talking about is this lowest level here of just getting hold of the data. And this data access problem becomes a lot more manageable if you can simply capture all of your data as these streams and put them in a central place. And that central place doesn't have to be Kafka, but Kafka does work pretty well for that. And once you have all of the data in place, then you can start thinking about the next level up of the infrastructure of how you can actually do processing on top of it and do interesting things, low latency response to the data that's occurring there. So let's talk a bit about interesting things you can do once you've pulled all of this data together into Kafka. One thing you can do is, well, you can send it to HDFS, or you can load it into a data warehouse. And in fact, that is a perfectly reasonable and perfectly good thing to do, because I'm not saying that any of the streaming stuff is going to replace data warehousing. If what you want to do is have a business analyst do ad hoc queries to explore some data set, it's totally the right tool, and keep using it. But if what you want is low latency response to some kind of events that are happening, then the streams are valuable. And the stream actually works really well as an ETL process into HDFS and data warehouses. So for example, there's this tool called Camus, which takes events out of Kafka and loads them into HDFS and does so very efficiently. Once you've got all of your data in streams, well, other things you can do is, for example, you can feed them into something like Elasticsearch, Kibana, search all of your logs. That's a kind of nice thing to be able to do for operational purposes. You could monitor things. So if you're simply sitting there as a passive consumer, you can start looking if there are any anomalies or odd circumstances that you should keep an eye on. That's obviously very useful for security purposes or fraud prevention and so on. You could use it to feed some real-time analytics systems, to some kind of real-time recommendation systems, maybe. All sorts of things suddenly become possible once you have the data available in streams. But what's more, you can even write these additional jobs which just sit there consuming streams and producing other streams. They're kind of like the transformation part of the ETL pipeline, except that they're decoupled and they're decentralized. You don't have one central ETL team whose job it is to write all of the transformation logic, but you can have various different jobs which just take in streams and produce other streams, maybe by joining a couple together or filtering or running a classifier over them, various other useful things you can do. And these can be independently developed by different teams. And for that purpose, at LinkedIn, we developed a stream processing framework called Samza. It's actually like conceptually a fairly simple thing. It basically lets you write code which consumes messages from streams, do interesting things like join streams together or aggregate them or filter them in some way, and then produce output streams or write the result to a database or things like that. the basic way how you use Samza is actually super simple. It's a low-level API at the moment, which consists of basically one Java method called process. A process method is called once for every message that comes in. And within that method, you can do whatever you want, like produce output messages or update some state, update some databases. Samza has some tooling that helps with that kind of thing. The interesting thing is that there's no real topology concept built into Samza as you get in other stream processing frameworks, because that we think of in Samza you would do by composing little jobs together. So you have these little red things would be Samza jobs, which are connected together with streams, with queues, which are just topics in Kafka. So you have one job which consumes some input topics from Kafka and writes it output topics back out to Kafka as other streams. And those, in turn, can then be consumed by some other job. So we're really using Kafka here as this kind of buffer between jobs. This has some really nice properties. One is that Kafka is durable. It writes everything to disk. It tries very, very hard not to lose any messages. So you get some very nice fault tolerance properties here that if one job dies or has some problem, the data is still there. You can take your time to bring it back up again, and it can then just continue from where it left off when it died. You decouple the performance of these different jobs. So if one job is going slow, it doesn't cause other upstream jobs to go slow, because Kafka can just buffer its input, can buffer a week or 2 weeks worth of input quite happily, because it's just using disk space and it's not expensive to buffer messages. And possibly the most interesting part here is the organizational scalability. So if you have Kafka as this kind of central hub for streams, you could call it a stream data platform, for example, then this becomes something that various different teams in an organization can organize themselves around. So now you have, for example, Team A, which maintains a user-facing website, and it has some web servers and some database, and as a side effect of serving requests, it writes some stuff to Kafka. It doesn't care who consumes that data. All it does is just send it off to Kafka as a stream, and then whoever wants can listen to that stream, tune into it. And then there's some other team who don't have any user-facing things. They only take that stream in, maybe consume several streams, do some interesting processing to it, produce some output streams. They're localizing just on their specific part of this whole data processing story. Then you have a third team, which maybe takes some of the data coming from streams and actually surfaces it to users, maybe through some kind of product features or search interface or whatever, and so on. You can keep building this up. And the very nice thing is that these teams are mostly decoupled from each other. They're basically using these streams, these topics in Kafka, as a communication interface, as the interface between teams. So data that is written to the stream by a job that's managed by one team is then consumed from that stream by a job managed by a different team. You can think of this a bit as an analogy. I don't know if this is dangerous territory, but I think of it as a bit similar to microservices, which is this big thing right now in the DevOps community on how do we structure applications such that it's not this one horrible monolithic beast that nobody likes to work with, but break it down into smaller components where each component can be managed and developed independently by a small team. And so these various parts can be evolved independently from each other, leading in the end to better agility, which is what we were talking about in the first place, making it easier to change the system and adapt it to changing requirements. Now, microservices are aimed really at the kind of synchronous request-response model, where you've got a user waiting to be served some response in their web browser or mobile app. And so you're doing low latency lookups in databases and returning synchronous responses. And I see stream processing as kind of the asynchronous twin of this, where for the data where it's not waiting on a user request, but you still want to handle it within reasonably low latency, say within a second or so. This is really where stream processing comes in. So at LinkedIn, this is really the thought process that people went through, and came up with some fairly basic structures for how to think about if you build this kind of central hub for streams, how do you make that an infrastructure that people can build on as easily as possible and enable people to just experiment and try new things, empower people? So part of that is simply making the data available, as we discussed. Part of that is this system being multi-tenant, so you don't have to order some servers and then wait for them to arrive before you can do some new experiment. There's simply a cluster of computing resources available. Anyone can submit a job to that, try experiment with it. If it works, great, you can productionize it. If not, throw it away again, no harm done. So being able to very quickly move in and out and allow people to just try new things in a self-service manner is super powerful. And you kind of get this bazaar of data sets then where, like, this team over here has combined a couple of data streams to produce some new composite stream, which they just need for their purposes. But then it turns out that actually this other team over there actually needs to do the same thing. So they can just talk directly to that other one and say, hey, look, you've already built this thing. Can we just reuse that stream? And they go, hey, yeah, sure, we're maintaining it anyway, so why not? So you don't need this central team whose job it is to figure out how data should be transformed, but instead you have much more flexible exchange within the organization. There's only a few ground rules that you need there, really. A few things that are worth organizing centrally are things like schema management, so that you have some kind of sanity about data encoding and formats, because if you have too many different formats, then people just waste all of their time serializing and deserializing and writing custom parsers for broken data formats. So standardizing on one data format, we've been recommending Avro to people because it's a great format, but you can choose JSON or whatever you like if you want, really. Standardizing on something is really valuable. Tracking who owns what data sets so that if something breaks, you know who to go to and ask them to fix it is very valuable. Of course, you need access control for security and privacy purposes, and you need some provenance tracking to see what data is flowing where and what is coming from where. But that's really just kind of basics. So the key idea here is that you can build these platforms in a way that's composable. This is a very good way of building infrastructure where you have these small components that can be evolved independently from each other, developed independently from each other by different teams, and have the simplest possible interface connecting them. Because if you have a really simple interface like a data stream using some defined schema, then it's much easier to keep developing the various parts upstream and downstream from that interface independently from each other. So using Kafka here as a way of simply connecting these things up works pretty well. The last thing I wanted to talk about here as another part of the infrastructure level of the pyramid is state. State is always a bit of a tricky one. That is the contents of databases, or databases, data storage systems in the wider sense. Say, for example, you have some kind of full-text search index, and it is currently serving some features of your website. And the way you add documents to this index is by consuming them from a stream. That's quite a nice way of doing it, because it means you've decoupled the people who want to write to the index from the people who are managing the index. So the stream simply becomes, again, this communication channel between different teams. And whenever messages get appended to the end of this Kafka topic, they simply get written to the index one at a time. And so this index is kept up to date. Whenever new messages are published, they get written to the index. As you can see, this works particularly nicely if your index is representing change data from a database, because every insert or update or delete here is a message, and so you can make sure that any write that happens in your database is also reflected in your search indexes. But now, what happens if you want to build a new index? So this is agility again. If you want to change your mind about how the data is structured, about how it's presented, or perhaps you want to add some additional data source to it in some way. If you want to take your existing data but present it in some new way, how do you go about doing that? Because you've built this huge index up, potentially over the course of years, and you can't simply go and just rewrite the entire thing because, well, A, the current application and users are depending on it. You can't rip it away from underneath them. B, you're tracking a moving target. So even if you could export the entire thing, rewrite it somehow, and then imported into a new database, then by the time you'd finished that conversion process, data has changed again. It's outdated again. So we found a really nice way of building new types of views onto existing data. And the way you would do that with something like Kafka is as follows. Start off with a completely empty index, a new server containing no data whatsoever. And assuming you've been building it off the log here, let's just assume for the time being that this log has never been truncated. It just contains all of the messages that ever happened. I'll relax that assumption in a minute. But for now, just assume that it's the entire history of everything ever. You can now just start consuming that at the beginning and gradually work your way forwards and write messages to this new index in the new format you want as you're going along. Until gradually your index fills up. And at some point, you reach the head of this long log, and you've got an up-to-date index. And it stays up-to-date just by continuing to consume it. But now you've rebuilt a completely fresh index, or this could be a cache or anything, with some new presentation of your existing data. So at the moment your users are reading from the old one, well, now you can gradually migrate them over to reading from the new one. You keep both indexes side by side so that if something goes wrong, you can always flip back to the old one. We want to make change as painless as possible. But if it does work and this new thing is the thing you want, then eventually, after you decide you don't need the old one anymore, you can just delete it, get rid of it, and keep this one. And so this gives us a really nice way of evolving systems in a way that Martin Fowler has this great way of putting it, of minimizing irreversibility. So you want every step you take along the way to be reversible very easily, so that in case something goes wrong, no harm is done. And this has this property very nicely. Okay, but I said there's this assumption that we're going to keep the entire history of all the events ever in Kafka, which is probably not a realistic thing to do. But there is something realistic that we can do, and this is actually supported as a feature in Kafka. And that is, especially if you're dealing with database change data, you can think of this data as having a key value structure. So where the key here is A, B, or C, and that's like the primary key of a table, or the key in a key value store. And what this thing here is doing is reflecting the sequence of writes that happen to particular keys over time. So reading left to right, so first A was set to 42, then B was set to 21, then A was set to 44, and so on. And if you are rebuilding a new index, a new cache onto this existing data, you don't really need to know all of the historic versions that some particular data item has gone through. You only need to know the latest value. So if that is the case, you can turn on a feature in Kafka called log compaction. And what this does is it allows you to garbage collect data by key. So Kafka guarantees that for any given key, the most recent message with that key will never be discarded. It'll always stay there. But if you have multiple messages with the same key, it's allowed to throw away the old ones and keep only the most recent. So this is very much like overwriting a value in a key value store, except that we've kind of sequenced the whole thing out as this sequential log of writes that happened over time. So the compaction step in this case would throw away the two old A messages, but keep the most recent A message and keep the B and C because there's no other messages with that key. And if you have this feature, then actually doing this reprocessing, starting from time 0 and crunching through the entire log, that becomes a feasible thing to do because the size of this thing is just the size it would be if you wrote all of this data into a key value store. So if you can keep the data in a key value store, you can also keep it in Kafka. So those are really the 3 points I wanted to make. There's number one is the first thing that we need to figure out with these systems is simply making the data available, because that's the bottom level of Maslow's hierarchy. If the data's not available, the fanciest infrastructure won't help. We can't do anything with it. But once we've made the data available, two key ideas really help us in building systems that are agile and allow us to respond quickly to change. One is having these small composable components which can be evolved independently from each other, which different teams can work on independently, and allowing this flexible data exchange between these different components through data streams in some kind of centralized streaming broker. And the other thing is if you have any kind of state, allowing you to rebuild that, because that means if something goes wrong, or if you change your mind about what that state should look like, you always have the ability to do that, and that's incredibly empowering. If you want to read more about this, there are a bunch of things. You can find the slides online. If you want to talk to me in person, I'll be doing office hours pretty much straight after this talk, 2:35, over in the East Wing at the O'Reilly booth. So I'd love to talk to any of you about any thoughts you may have about this. There's my book again, and hopefully we have a little bit of time for questions.
Hi. Just wondering, do you need very fast local disk for your Kafka servers?
It helps, though Kafka was originally designed for spinning disks, and it works reasonably well on those. I think LinkedIn runs Kafka on SSDs, which helps certainly if you've got, if all of the consumers are at the late just consuming from head, then you're basically only writing from disk. The disk cache does everything else, so the data being read is actually all being read from memory. So in that case, the type of disk hardly matters. The fast random access property of SSDs is mostly useful if you've got clients doing a lot of kind of reprocessing stuff, like jumping back in time and crunching through old data. In that case, you get random seeks, which get slower on spinning disks. So for that kind of thing, SSDs are useful. But you don't need any particular hardware. It's all commodity hardware.
Does Kafka, sorry, I'm here.
Oh, yes.
Does Kafka provide any sort of access control for topics, or is it an API so you can hook in a library or something?
Access, like ACLs or security?
Yes, I'm just thinking if there's a stream, you had your slide with different teams.
Yes.
In my company, some teams could see some data and not others and that sort of thing. So.
Yes, that is currently a limitation with Kafka. So people are working on adding authentication and access control, but I believe it's not quite there yet. It is going to come. But for now, you basically have to do network-level access control, which kind of defeats the point of having a central repository. I get that.
Hi. I'd like to ask a question about if you're in a situation where you don't have available the sort of development skills that you seem to need to use a lot of these tools. Are you seeing any of the commercial vendors taking interest in this as a route?
To be honest, I don't actually know too much about what commercial vendors are doing here because I've been very much on the open source side of things all of the time. I mean, for Kafka, there's starting to be commercial support. So there's a company founded called Confluent, which is a couple of engineers from LinkedIn who actually designed and built Kafka. And I think they're working on a commercial distribution for that. Apart from that, I think like some of the Hadoop vendors are including Kafka in their distributions as well. So I think it's gradually getting there. How all of this compares to the traditional enterprise messaging products, I think that's a much bigger question. So that maybe be something to discuss offline.
So a question here. You talked about log compaction in Kafka, and say if you wanted all events and you couldn't use compaction, and if you were only storing a couple of weeks of events in Kafka, and you were using HDFS as an active archival storage, is there a way to replay those events from HDFS back as streams into Kafka and then repopulate the entire index in that case?
That's actually a really good idea. There's no HDFS consumer as such built into Samza at the moment, I think, but it would be a really easy thing to write. I think the main reason that one hasn't been added to the standard distribution is that nobody's quite sure what the right structure for it would be, like what is the right data layout to assume so that you have a correspondence between the Kafka view of streams and the HDFS view of streams. And then you'd have to probably have some kind of cutover point as well. So at some point you then switch over from consuming from HDFS and then get the latest data from Kafka maybe. So there's some thinking that needs to happen there. But in principle, yes, this is a totally reasonable thing to do.
Okay, we'll do one more and then move off to the office hours.
Okay, absolutely.
For log compaction, you mentioned you only get the latest key, or what is the guarantee you have there in terms of what keys you may get and what happens with the other replicas?
So the log compaction is consistent across replicas, I believe. So in Kafka, all of the reading and writing happens from the leader replica for a partition anyway. And I think the leader is in charge of doing the compaction. So you shouldn't end up with disparities across replicas there. In terms of when the compaction happens, there's basically no guarantee. So if you're reading a compacted topic, you may or may not see duplicates. If you reread the same data at some later point, there may be fewer duplicates than you saw previously. It's very hard to make firm guarantees about that. So basically, the only guarantee is that the latest message will be there. OK, thanks very much.